Okay, so welcome back, everyone. Next up, we're going to have a talk by Stefanie Jegelka at MIT on learning in graph neural networks for algorithms. Okay, thank you, Stefanie.
Thank you very much. So yeah, as Jelani said, I'll talk about learning in graph neural networks today, which has become a very popular subtopic in deep learning these days. And this is joint work with a number of people. In particular, I'd like to point out my PhD student, ReLu, who just graduated. So let me first clarify the setup a little bit. So the kinds of problems I'll be looking at is less about learning parts or configurations of algorithms, but actually learning the full algorithm. So basically the input to our neural network will be, for example, a graph, and the output is, for example, the value of the shortest path in that graph. And so the actual, like the full algorithm end to end is supposed to be implemented as a neural network. So this is probably the hardest kind of task. And we are trying to minimize an expected loss over a test distribution. So this is the setup. And what we are given for training is pairs of inputs and solutions that we want to learn. So what I'm interested in this talk is how well do neural networks generally, and graph neural networks in particular, learn such algorithmic tasks? And what are the things that it depends on, and can we try to understand and formalize them better? And I look at this from two different perspectives or questions. The first one will be generalization in the usual sense of generalization in machine learning, meaning I'm given instances drawn from a training distribution, and I'll be looking at test instances from the same distribution as the training distribution. So basically, it's just different samples from the same distribution. And in particular, there will be interested in looking at the influence of different architectural structures of the neural network. And second, what is also of big interest these days is actually going beyond that training distribution, so having distribution shifts. And what this means, for example, in learning combinatorial algorithms is that you're training your neural network on graphs of a certain size, and you're hoping that it will also generalize to graphs of a different size. And that is actually not always true. So this extrapolation and interpolation or generalization are a little bit different in what affects them. Some things are common, so we'll go from one to the other. So let's start with generalization. But before all, I would like to bring everyone on the same boat and explain to you what is a graph neural network. So yeah, and in particular, we'll have to care about when we think about learning neural networks. In neural networks, we'll have to actually think about various different things. So one is the model architecture, what kinds of things am I learning, what's the geometry of my data, plus how am I actually training this neural network? Because usually I'm not reaching the minimum of my empirical risk. So first, let's look at a specific type of neural network architecture that has been very popular for learning representations of graphs. And these are graph neural networks. So what does a graph neural network do? In a nutshell, what it's trying to do is you're giving it this graph, and the graph has some attribute vectors for each node, which is some information about the node. So in your social network, this may be like the interests or some demographics of the people. And you're given the connections, of course, of the nodes. And then what you want to represent is both all the attribute information that you have about nodes and possibly also on the edges, and the structural information of the graph. So you want to somehow encode all of this together in the sense that similar graphs in the right sense of similar would end up together in some vector space, that's your output space. So the way that graph neural networks do this is in a two-stage approach. First, you learn an encoding of the neighborhood of each of the nodes. So that way you can make predictions also on each of the nodes by themselves. And if you want a prediction on the full graph, you're going to aggregate that set of node representations into a graph embedding. So pictorially, what this does is basically for each of the nodes, it looks at the node's neighborhood and encodes the structure and the information it has about that neighborhood. Each node gets a feature vector, that's the representation of the node. And then you're taking that set of feature vectors and doing what's called an aggregation or readout and combining those into an encoding of the full graph. When you do this encoding, it's important that there's no specific order between the nodes, so that function has to be permutation invariant. So a simple way to do this would be to take an average, or you can do something a bit more sophisticated than that. But let's turn to how you actually encode these neighborhoods. So how do you get to these vectors that encode each neighborhood? And the way this is typically done is via message passing. So it's in some sense, a graph neural network is nothing else than a learnable message passing algorithm. So to look at an example, let's say we wanted to compute the encoding or embedding of that red node V. So what you do is you go in rounds, and in each round, node V collects the feature vectors of its neighbors and encodes those into a message. So that encoding is basically, it's called an aggregation function. It takes a set of vectors, one vector from each of the neighbors, and that's the current feature encoding of that neighbor. And then you're taking these and mapping them to a single vector, that's your message. And this aggregation function is what you learn. And it has to be permutation invariant too, because there's no order between the neighbors. And I'll show you what this looks like. Essentially, you can think of doing a nonlinear operation on each of the neighbors' vectors and averaging or summing that up. That's a typical procedure. And then once you have that message, you combine it with the current nodes representation to update the current nodes representation. And that is done, can be as simple as a weighted average where you're learning the weights. So this is the general scheme, and each of the nodes does this in parallel. And as I said, what you're actually learning is how you do this aggregation from the neighbors. So how are you processing the information from your neighbors? And as you go, of course, in more and more rounds, your neighbors have collected information from their neighbors. So after 2 rounds, you have information from a 2-hop neighborhood, etc., etc. So the more rounds you go, the larger is the neighborhood you're encoding. So what does this aggregation function look like? Often, or in a very general form, it can look as follows here, that now I'm looking at, I hope you can see my cursor, I'm looking at basically each of the neighbors individually and applying a nonlinear function to the center node, the neighbor, and the edge weight if I want. And this function that I'm applying is a learnable small neural network. So this MLP is a multilinear perceptron. It's essentially a small, fully connected neural network. And then I'm summing this up. So this is the kind of functions. This is sort of the most general, most expressive way I can do this aggregation function. Typically, these are not very deep, but it's a neural network. So you can already see, you can actually view this graph neural network either as a learnable message passing algorithm, or actually, as we'll see on the next slide, a configuration of learnable modules where each of the modules is this aggregation function. And this is the viewpoint we'll take through. So how can we view this message passing thing as a neural network? And here is another viewpoint in it where we are just unrolling these message passing iterations. So let's say we want to compute the encoding of that yellow node A. So node A is collecting information from its neighbors, which are B, C, and D. And this aggregation function here is just depicted as a gray box. So that's the thing you're learning. And each of the nodes is using the same gray box. Now, in the previous iteration, node B collected information from its neighbors. So these are the states or the feature vectors from the previous iteration. And likewise the neighbors. So if I unroll this, I get this so-called computation tree, which shows me the computational structure of what this algorithm is actually doing. And now if I do it this way, it looks a little bit like layers. So these are essentially the layers of my graph neural network, where in each layer, I actually have these gray boxes that are the same, they are shared weights. And these are the things that I'm learning. So each layer in some sense has these small neural networks in them. So you see, this is a neural network, but it actually is flexible in the degree of the connections. And these, like the branching factor of this tree here, depends on the connectivity of my input graph. So this is a high-level picture of what a graph neural network does. We can view it via these trees. We can view it just as a message passing algorithm. So now that we have a rough picture of what is a graph neural network, I want to go back to my two questions. So the first one is, what does generalization in graph neural networks depend on? Can we quantify that? And as Ellen said in her talk, generalization means I'm optimizing some loss function on my training data set, and I would hope that I'm performing well on the test data set. So it's basically the gap between training and test performance. And there have been a number of recent works looking at generalization bounds for graph neural networks. So the most general ones are bounds that depend essentially on complexity, like we see dimension, Rademacher complexity, etc. So these are the first ones. Then there's some that also take into account the learning algorithm, which are the ones, for example, based on neural attention kernel frameworks. And what I want to focus on today is taking into account even more of the structure of the problem, actually the architecture and the task structure. But before I go to this last one that also looks at sort of the inductive biases and their interplay with the task, let me first show you what these norm-based bounds here generally look like. So I'll just show you some bounds from our own work from this paper in ICML 2020. So here is what these bounds typically look like. So this is roughly the gap between training and test error that you can expect. And they depend on a number of different things here. So little m is the number of training examples. So as I get more, the bound shrinks, of course. And then they depend on the depth. So now they actually analyze essentially this computation tree. You can reduce the complexity of the graph neural network to the complexity of that computation tree. So you look at the depth of the tree and essentially the branch out factor and the complexity sort of these boxes. And this is in this percolation constant here. It's basically bounds on the weight matrices and Lipschitz constants. So overall, it depends on those things like depth and smoothness, etc. But and they are very general. But if we actually look at many of the algorithmic tasks we want to learn, there's actually much more structure in the problem that we could potentially explore. So I want to take a step back and first of all, like define these algorithmic tasks, the right range of tasks I'm looking at, and look at the comparison of different network architectures, not only graph neural networks, and how they differ and what this may actually depend on. So the general type of tasks we're looking at here is what are also called algorithmic reasoning tasks. So they could be something like learning, for example, a shortest path algorithm like this type here, which is maybe the most complex one, where you're given an input graph and say, what is the shortest path? But they could also be predicting the next state of a physical system. So basically forecasting simulations, understanding physics, or much simpler relational questions about different objects. So the common thing to all of these is that they can actually be solved with some kind of algorithm. Now, since this is called like these algorithmic reasoning tasks, there's a good survey paper here that talks about how general approaches to solving these. A general setup for this is that you actually have some universe of items that you're given and you want to answer a question about these items. So they could be these physical objects that are interacting, they could be the nodes in your graph and the edges in your graph. We are abstracting away all the visual perception and we are assuming we are given a set of representations. Each of the items in my input, I have a representation of that item. And I'm only looking basically at what neural network should I deploy here to get a neural network that can answer basically questions like that. And now basically the key question is what could go into the so-called reasoning network that takes a set of object representations and computes basically the answer. And there's many different options, of course, available that I could use here. So as I said, let's first think about a few different architectures for these kinds of tasks. And the first one would be just take a fully connected neural network. So this is my MLP here, which is one big gray box where every between the layers, everything is interconnected, and just basically concatenate these representations of my input, send them through a fully connected network. This in principle works. It has one drawback, that in what order should I input the representations of my objects? There's no specific order, so I actually want to be invariant to that order. And this specific architecture doesn't actually respect that. It has to essentially learn it. So let's become a little bit better and use what are called deep sets. So what they do in a nutshell is that they take each of the items that I have for my input, they apply a small neural network, then they sum up the results, and then they apply another small neural network. So what you're learning is essentially these two neural networks. And they are here depicted by these gray boxes. So that's the deep set architecture. It already has this permutation invariance built in. So it doesn't have to learn that you should be invariant to what the order of which these items come. And now the last thing that people have looked at is, so here I actually don't have a graph. I just have a set of inputs and I want to compute something relational question about these. Like maybe these are planets that are moving around and I want to predict where they are going, or I just want to compare these objects. But anyways, even if you don't have a graph, you use a graph neural network. So you just build a fully connected graph and you say everything is connected with everything. And now you just use that graph neural network architecture that I outlined to you a few slides ago. So what does this do? Just as a reminder, essentially what it does is it does pairwise comparison. So instead of like processing each item at once and then summing it up and processing again, it essentially processes pairs, all possible pairs. And it does this consecutively. So this is essentially what it does. It does this pairwise processing, sums up the results for each node, and does this over and over again. And finally, you just do like one more of these aggregations to get the output. So in some sense, it's sort of a configuration of many of these little deep sets architectures. Each of these is like an aggregation function in a graph neural network. So we have these three different architectures, more and more structured. And now what you can show is by expressive power, if you just look at set functions, functions over sets of vectors, if one of these architectures can represent it, the others can also, in principle. So just by mere expressive power, there's actually no difference, roughly, between these architectures at a high level. But if you actually look at them empirically and try to train them on these relational reasoning tasks, there's big empirical differences between them. So typically, the more structured architectures work much better than this fully connected network. And maybe this doesn't come as a surprise, because, yeah, you have this thing in your mind that maybe this has the right inductive biases. But what exactly is this inductive bias? So let's try to think about this a little bit more. And now the idea is that, well, what we are actually aiming to learn is something that's close to an algorithm. And what is an algorithm? An algorithm is essentially a structured arrangement of subroutines. Like often they have for loops, and in each loop you do something you call like a subroutine or so. So that's my algorithm. And this is the computational structure of an algorithm that solves the task. Now, what about my neural network that learns it? If I look at the graph neural network, it actually also induces a computational structure via these computation trees. So I can think of my graph neural network or any, like the deep sets or so, any neural network that it has this structured arrangements of specific building blocks that I can learn as essentially a structured arrangement of learnable modules. And in the graph neural network, these are my aggregation functions, the small MLPs that are in there. And now the high level idea is if these match up by structure, then all I have to learn is nothing about the structure of the algorithm and just basically the subroutines. And if they're simple enough, then presumably the learning task should be much simpler. So this is the high level idea. Now, let me show you an example that why specifically graph neural networks have this nice computational structure that fits many of these algorithms that you may be interested in learning in these tasks that I showed. And so here, let's use the shortest path as the running example, because hopefully everyone knows the shortest path algorithm. So on the left, you see the Bellman-Ford algorithm, which is an algorithm for computing shortest paths. So what this does is it goes in rounds, and in each round, in each iteration, it looks at all the nodes, and basically for each node, the current state is the shortest path through the target. And now you look at your neighbors, and you look via this neighbor, could I actually reach the target quicker? So you just look at basically the cost is the distance to the neighbor via the edge weights, and then you just look at the neighbor state. So at the end of the day, like for each neighbor, you do a simple computation, looking at the neighbor states, adding the edge weight to the neighbor. So now if you look at your graph neural network, it actually has the same computational structure up to like the number of levels in the graph neural network should be close to the number of iterations in Bellman-Ford. So for each node in the graph, you do this aggregation operation. And now if basically your aggregation operation is mimicking this step, then all you really have to learn is an addition and a sub-min over the neighbors. And that should be presumably a much simpler function to learn than the entire for loop here, because they match so nicely in computational structure. So you can also quantify this, and I'll show you in a second how. But the high level, so this is what we call algorithmic alignment, is that a high level, the computational structure of the graph neural network and the target algorithm for computing the solution match up in the sense that all that you basically can mimic the algorithm by learning simple functions. So here, this is just a simple function that you learn. Now, how does this actually affect results empirically? So presumably here, the Bellman-Ford matches the graph neural network very well, but not a fully connected network, because basically to mimic that for loop in the fully connected network, you have to learn a lot of sparsity and invariances, etc. So this is also reflected empirically. So here are examples of test errors on shortest path tasks on relatively small graphs. And you see that basically this is the test accuracy here. So smaller is better, no, higher is better, sorry. So fully connected networks and deep sets basically don't learn it at all. And then the graph neural networks, once you have reached a certain depth, they actually learn the task well. And if you look at shortest path, you have to have a certain minimum number of iteration. Actually, what you need is half the length of the shortest path. Then you can actually essentially implement a bidirectional version of Bellman-Ford. And this is kind of reflected here. So as I said, these are short, small graphs in this example. So basically length 3 or 4 was half the length of the shortest path in this graph. But this is one empirical evidence. You can see this on other tasks as well. Let me try to formalize this a little bit more. And this is also the basis for the second half of my talk. So more generally, the idea of alignment extends basically between graph neural networks and many dynamic programming tasks, where you basically have a state of each item, and then you update that state via a simple function that's a function of the other item's previous states. And so K here is the iteration, and J is the other items. And now basically you can implement this via your graph neural network by having this small feed-forward neural network, the sum over the small feed-forward networks, mimicking this dynamic programming update. And since this is in principle a universal approximator, it should be able to do this. But often, then that's the key thing, these DP updates are not so complicated. Like in the shortest path, that's not a complicated function, this update. And many of the algorithmic and physical reasoning tasks that people have been looking at in the recent deep learning literature have this flavor of a dynamic program with relatively simple updates. So many of these physical simulations, they are basically interactions, updates that depend on distances or so, but they are not very, very complicated functions. So now let's try to formalize this a little bit. So we say that a neural network, M epsilon delta, aligns with an algorithm if the neural network can mimic this algorithm while implementing simple functions in its learnable modules. And so basically what you now count for the complexity is the number of modules. So if you have shared modules, you would count it only once, and how complicated it is to learn the function in each module by itself in a PAG learning framework. So basically that M quantifies sort of essentially how complicated it would be to learn each of these modules individually. And then this delta and epsilon mean that then with probability 1 minus delta, you get an error of smaller than epsilon. So this is how we can actually formalize the alignment. And basically, if the architectures don't align that well, the idea is that these modules that you'd have to learn are much more complicated. Like maybe they have to implement part of a for loop or something like that. And then it's much more complicated. So what does it gain us for learning? What you can basically show is, under somewhat simplifying assumptions, that if you basically have this algorithmic alignment, then the overall complexity of the task can be measured by the complexity of the modules that you have to learn. And so this actually, via this idea, you can actually prove some gaps, show some gaps between different architectures in simple functions. This, I have to say, this result does make a few simplifying assumptions, and the strongest being that you have to do layer-wise training, so you need feedback in each layer, which I would like to remove. But there is actually also evidence in the empirical literature where they use exactly that kind of training. And actually those empirical results reflect a lot of what our theory says. So this algorithmic alignment, I would like you to keep it in mind, is essentially the idea that I can mimic the target algorithm via simple learnable modules, because each module doesn't have to capture too much of the, just a small part of the algorithm, a simple subroutine, and not a big part of the algorithm. So the computational structures match. And this we will carry over when we look at extrapolation. So next, I would like to go on and talk about extrapolation. And what we'll see here is that this notion of algorithmic alignment also it's actually used in a lot of the practical architectures, but what is important is actually more than that. So you have to be more careful about the nonlinearities in your task. So first of all, extrapolation has been an issue in recent deep learning, especially in these so-called reasoning tasks, where, for example, you're looking at having the network solve IQ tests, where it has to basically say what comes here in this last square, where it has to generalize across shape, color, and number of objects and extrapolate on these axes. When you look at physical reasoning tasks, you may want to extrapolate the position of the items, the mass, or the number of objects, for example, when you want to forecast what's happening next. There's questions in mathematical reasoning where you look at the length or the number range of the questions that are posed. And what we'll be interested in is learning graph algorithms. So we were interested in what would the network do if now I give it different distributions of graphs, meaning different degrees, different graph sizes, different structures, etc. But what I'll be telling you, actually also the main ideas hold for these other tasks as well. So basically the question, as I said, is, does the graph neural network generalize to graphs with different structures, different degrees, if I train it on a specific distribution of graphs? And this is relevant for obvious reasons. If you think it has learned an algorithm, it better also generalize to other graphs if it's really implementing that algorithm. But this is actually not always necessarily true. So what prior empirical works have shown is that in some cases, we can actually successfully extrapolate to larger graphs, but in many cases, this is also difficult. So this has been looked at for learning simulations. It has been looked at for learning inference algorithms, like graphical model inference algorithms, etc., where often the performance decays. But sometimes you can do it, and the question is under which condition. Also, actually, if you look at the literature for fully connected networks, they typically are very restricted out of distribution. So basically, if you go away from the training data set. So what we are really looking at here is we're looking at a test data set that is potentially completely outside of the support of your training distribution. And so basically, the thing is that these MLPs are the building blocks for graph neural networks. These are my modules. And if my modules fail out of distribution, how can the graph neural network extrapolate well? And let's take a closer look at that. So let's look at basically one of these learnable modules, one of these aggregation functions. So let's look at first a feed-forward, fully connected ReLu network and see what it does if I do a distribution shift. I get basically look at data that is very different from my training data. And this is here a very simple example in like up to 8 dimensions where I have nonlinear and linear functions and piecewise linear functions. And this is the y-axis is the error. And what you see is that basically on the linear function, sometimes it succeeds. So lower is better here. In the directionally piecewise linear functions, sometimes it succeeds, but on all the nonlinear functions, it generally doesn't, it implements something else than what you implement in the training distribution. And this is actually something you can explain. And it helps us understand what the graph neural network is going to do because it's made up of these little building blocks that are behaving in this way. So why does the fully connected network behave like this? Can we quantify that? So here is the same thing, but in a one-dimensional picture to illustrate what's happening. So here in this specific simple example, I have a sine curve. That's my training data. And I want the network to learn the sine curve. And I'm giving it training data and within this blue box. And then I look, what is it doing outside that blue box? And of course, it hasn't seen any data. It doesn't know that this is a sine curve. Inside the training data, it's a universal approximator. If you have enough samples, it's going to approximate well that sine function. Outside of the training data, it's actually implementing a piecewise linear function, a directionally linear function. And this happens not only in one dimension, it happens only in also in higher dimensions. And formally, what is happening is as you're going away from your data, fairly quickly, the neural network is implementing a directionally linear functions, which is linear along directions away from your training data. And hence, basically, anything that is like this, directionally linear function or linear function, it can extrapolate it well because as long as it has learned that all it should be doing is a linear function. But anything that's nonlinear, it doesn't do it. And the reason is that essentially outside of the training data, it hasn't seen any data. It's going to do whatever is basically built into the architecture. And here it is because of the ReLu. So how do you actually analyze this? And this analysis here is for the neural tangent kernel framework, which is admittedly a bit simplified, but you saw it actually holds also for deeper architectures and like finite size architectures. So the way you analyze this is that you look at basically the neural tangent kernel framework, which takes into account the training algorithm. And it looks essentially at a linearization of the neural network. And at this linearization of the neural network behaves like a kernel method. And this is essentially, it looks at the tangent essentially of this neural network. Now, what we can show is that it basically finds a function in the function space defined by this kernel. And it finds the minimum norm solution in this function space. And then we look at what does this minimum norm solution look like. And now basically each function in this function space can be looked at via a feature map. So essentially what this neural network does is it takes the data and projects it into a high dimensional, infinite dimensional space and does basically a linear function in that space. So if you look at what this feature map looks like, it has exactly these W's here are like it's infinitely many repetitions of this thing with different W's. W's are Gaussian random vectors. And you see this actually basically already has this piecewise linear structure in here. And it's centered around the training data, roughly. This is to give you an intuition where this actually comes from for the ReLu network. The second thing is, so this is just that, okay, it implements some piecewise linear function. And now the question is, well, let's say we actually really only wanted to learn a linear function. That's it. Does it actually do that? Now it's a ReLu network. It can do many different piecewise linear functions. So to actually learn the linear function that we want, it has to have enough information to make it identifiable. So basically, we need enough information in the data. And here this means we basically need information in all directions of the training data. And you can show this theoretically and empirically. But I wanted to go back and see what does it actually mean for my graph neural networks. So first, we can only extrapolate linear functions, essentially directionally linear functions in each of my modules. And the second thing is we have some conditions on the training data geometry to actually find the kind, even if I want a linear function, to find the kind of linear function, the right linear function. So let's look at the first one, that we only can implement linear functions. And let's look at our running example again, the shortest path. So what I said is what you essentially, you can learn shortest path by if each aggregation function implements this dynamic programming update, where you take the min over your neighbors and add the edge weight to the neighbor. So the typical sum aggregation GNN, basically this part, the sum and then the nonlinearities together have to implement this minimum and the sum. And since the MLP is a universal approximator, you can do that in general, but it has to be a nonlinear function because you have to implement the min with a sum. Now, if you look at the recent papers that actually successfully extrapolate, they use a min instead of a sum. And the key idea is that here you actually only have to learn a linear function and not a nonlinear function. And now this leads us to actually restricting our definition of algorithmic alignment to linear algorithmic alignment, where you basically have to be able to mimic your algorithm with linear learnable functions, not nonlinear learnable functions, because that will make a difference for extrapolation. So in short, for interpolation, when training and test are from the same distribution, it doesn't matter because your neural network will implement the right nonlinear function. But outside of the training distribution, you're going to implement essentially a linear function. So all you can really do is you can basically hope that you're learning the right linear function, and that will be able to extrapolate. So basically that means you have to encode all the nonlinearities either in the architecture or in the initial input representation. And this difference between interpolation and extrapolation is what you see empirically too. So here are the sum versus min pooling, and in interpolation there's hardly any difference, but when you go out of the distribution, basically only the one that essentially has to learn the linear function extrapolates well and the other one doesn't. And this is essentially one way to understand some of the recent developments in deep learning for these kinds of tasks, is that essentially the architectures are set up in a way that the learnable parts are mostly linear functions. So you basically have implemented the nonlinearities in the right way in your architecture. The other thing you can do is actually hand design or learn, do maybe pre-training to learn a better representation of your inputs, that what you have to learn is more linear. So I'm running a little bit out of time, so I'm not going to go into detail of that. And the last thing I wanted to say is that the last ingredient that we have also is that it depends on the distribution of the training data. And I showed you this example with a linear function that has to be linear, the same linear function in all directions. You see similar patterns when you train on graphs. So you need enough diversity essentially in the input graphs to actually generalize to other types of graphs. So basically enough diversity in the degree distribution, etc. And you can formalize that in simple cases, as we see here for max degree. So I'd like to end here and summarize. So what we saw is that an analysis of generalization and extrapolation of graph neural networks with a focus on learning algorithmic tasks, where we saw that the architecture's interplay with the task is very important, but also when we look at extrapolation, in addition, the form of the nonlinearities and where they occur. So thank you very much.
Thank you very much, Stefanie. Do we have any questions before Anna begins her talk?
So I do have a question, but this is one of those dumb questions, I guess, but I'm going to ask them anyway. So there was a recent article in a Quanta magazine about neural networks having difficulty with, like basic concepts such as sameness, like whether two given pictures have the same structure or not. Yeah, and I guess the question is, like it seems that your results might potentially shed some light on this. But I guess if you haven't seen this article, it's probably hard to answer this question.
Yeah, I haven't seen it. I'll take a look at it if you send me the link, and maybe then I can say something smarter about it.
Okay. Yeah, I just posted it in the chat.
Okay, good.
Yeah, cool. Yeah, it also has to do with the extrapolation, right? So, cool.
All right, great. Thanks again, Stefanie.